So guys, I know that we said jokingly months ago in January, tomorrow's the AP test. Well, guys, now it's really starting to me to feel like tomorrow's the AP test. So what I want to do is I want to lay out for you what the rest of this year is going to look like. But here's the hazard. I do this every year. We come back after spring break. We lay out the plan. We'll talk about the plan in lab, third period, but today just this period. But guys, the problem is that many times people's eyes immediately jump to what's after the test. And guys, we need to stay focused on what's before the test. So here's what we're going to do. I know that we talked previously about this idea that we were going to try to stack things up so that we were done by spring break. We did leverage one day to do KSP stuff on a Wednesday. But guys, I just decided I didn't want to do that, which means we are going to spend these next 2 days doing electrochemistry. Typically, electrochemistry is a 5-day unit, including the test. What I've decided to do was to get to the nitty-gritty of electrochemistry and then not do a test. Okay? So guys, understand that what that means is the test that you have in your possession is the only test you're going to take this quarter, right? And you don't get to rewrite it because you're doing it one and done in groups. So guys, understand we said that thing's due on Thursday. It is still due on Thursday. But guys, understand that thing's going to be weighted more significantly because it's the only test we're going to do this quarter. Okay, so please keep that in mind. So what we're going to do then, guys, is today we're going to talk about balancing redox reactions. You will not see this on the test in its entirety, but I still teach it because when you get to college, it's horrible, and it's nice to have learned it from me first. Then, guys, on Thursday, we're going to talk about batteries, which is fascinating. You're going to love the chemistry of this. And then we're done. We're done with electrochemistry. Then, guys, following that, we're going to go spend next Monday, and it's just going to be a day talking about what the test is going to look like. Then, guys, we're going to take 2 full AP tests. On the 22nd, we'll do the multiple choice, and then on the 26th, we will do the free response of 1 test. Then we'll rinse and repeat on the 29th, and then the 5th. Then, guys, the 6th, we are going to have a day where it'll be maybe small groups. It'll be you thinking through things, some last-minute fine-tuning. And then, guys, the 7th is the test, which is functionally tomorrow, right? Then, guys, following that, we are on short time. What I always do is I don't plan anything for the week after. Well, my test is always the first week. It used to be the first Monday, but that's not the case anymore. But guys, I am not planning anything during this week. What I want to do is I want to give you the 10th and the 13th to study for your other AP tests. Okay? So I have nothing planned on the 10th and the 13th. But guys, please understand the obligation is this. After our test, you are still my student. And you will be here second and third periods for the remainder of the year. So the 10th and 13th, I leave open simply to respect your time and your needs relative to other tests. Then, guys, the 17th and the 20th, we have a long-standing tradition of having a lovely little end-of-the-year celebration, which generally sends everybody home having eaten so much that we want to just curl up in a ball and die. And so that'll either be the 17th or the 20th. Yeah, so we're actually learning more. So, guys, we don't yet know, unless you know more than I do, when Lagoon Day is. I can't believe we're having it at all. I believe that that's the case, that Lagoon Day is still happening. Is that true? Then guys, graduation, and I don't know what you know, so we'll just talk about it. Graduation is on the 25th, and it's up at the Riot. It's up at Rio Tinto Stadium. So we graduate on the 25th. I have no idea if I'm going to see you on the 24th. I'm planning for not. There is some talk that these days could be finals. I don't know. I don't even know what that means anymore. So I'm thinking probably the 17th will be our end of the year gathering, and then we'll just go from there. So, questions about any of the calendar stuff? You guys, yeah? So the way that, and we'll talk more about this on the Monday where we sort of get to know the test. But what they like to do is they like to try to start the test by 8. And so you show up at 7:30. Typically my students get together, usually in my room, make sacrifices to the chemistry gods, do their little chemistry rain dance, and then head down to the test. Exactly. It's all about sacrificing to idols. And then, Ronnie, we'll always have a break between the multiple choice and the free response, and I'll have breakfast for you. So those sorts of things. Light finger foods. Unlike Coxon, who for calculus buys everybody Champs, and Ellingford, well, he struggles. You appreciate how eccentric our good friend Mr. Ellingford is. I'm not Ellingford or Coxon. So it's typically just stuff I pick up at Costco. So, guys, other questions about the calendar? Okay, so guys, today we are going to start one of 2 days about electrochemistry. Today is conceptual. Next time does get into the math of batteries. But guys, grab something you can take notes on, and we're going to dig in. So guys, Beard is gone. I know, right? So normally this is my rotation. So usually at Thanksgiving, I promise you not for No Shave November, I would grow a beard to keep my face warm for ski season. And then in the spring, I would shave it for cycling. And then COVID happened, and for the first time in forever, I had a beard all summer, frankly, because I just wanted to crawl under a rock and die, and I didn't have the energy to even shave. I know, exactly, right? And so this isn't unusual. The fact that I started the school year with a beard is unusual. It's normally November to spring break, and it had to go. So, yeah, it gone. It gone. All right, guys. Redox chemistry. Here we go. So, guys, chapter 20, I know that you've summarized this. What we're going to do in the next couple days is we are going to tease out the big ideas that you need to understand. So, you may remember, you don't remember. I wish you remembered, but you don't remember. Chapter 4. Guys, don't look at it. But way, way, way back when, and I know this is a little anticlimactic given what our year has been, but guys, the very first unit that we did this year was about aqueous chemistry. And we learned about, remember this, net ionic equations? And we learned about spectators, and we learned about precipitation reactions, and we learned about acid-base reactions, and we learned about gas-forming acid-base reactions. And then, guys, we did one little itty-bitty day when we learned about oxidation reduction. And I said, guys, we're just going to learn this today, back in September, just enough so that it's out there. But when we come back to it again, it's going to be the end of the year. And that's now. Guys, we are now bookending our year by starting with oxidation reduction, and now we're ending with oxidation reduction. Now again, guys, there are things in chapter 20 that we are not going to cover. There will probably be stuff on the AP test that will be out of chapter 20 that we're not going to cover. But guys, you understand that, right? You're not shooting for 100% on the AP test. There will be stuff on the AP test that you're going to read this question and go, I've never heard of this before. Right? Some of you have that experience on our unit tests, and that's bad, but guys, understand there's stuff on the AP test, even if we weren't skipping part of chapter 20, that you just won't have heard of before. Another example is organic chemistry. There is a little bit of it on the AP test, but so little that it's not worth our time. But guys, we are going to chew on the big chunks, and this is one of those too. So guys, oxidation reduction chemistry, let's summarize, and then we'll get into it. So guys, it starts like this. This is it. All that oxidation reduction is a transfer of electrons. Every year I have somebody say, oh, is this like acid-base chemistry? Where in acid-base chemistry it's just a transfer of protons? The answer is kind of, but don't run with that too far. But guys, in the same way that we think about acid-base chemistry as an acid losing a hydrogen and a base picking it up, now instead of tracing hydrogens, we're chasing electrons. But guys, the question then becomes, how do we know when electrons move? And the answer is, we don't. Guys, obviously we can't see electrons. We can't go into lab and do chemistry and watch electrons move. So what we actually look for is evidence of the moving of electrons, and we find that through changes in charge. So guys, fundamentally, that's what you're doing when you're doing redox chemistry, is you are tracking changes in charge. So guys, it's at this point that you need to know the terminology. I would strongly encourage you, if you're not taking notes, to write this down. Electrons are transferred from the atom that is oxidized to the atom that is reduced. Now guys, here's the deal. And I would be surprised if any of you get here this year, because we are kind of clamping down on the amount of exposure we have to this. But guys, you need to know these two terms. You need to know oxidized, you need to know reduced. And what I tell my students every year is that you need to know these terms well enough that you don't have to think about them. Which then brings up an interesting idea. All of you guys have either siblings or friends that are missionaries, right? Off in other places. So guys, if you know somebody that's a missionary, if they're serving in a place where they're not speaking English, almost every missionary has a story that was the moment in their life when they realized they had really learned the language of where they're serving. What happens on that magic day? Come on, you guys have heard these stories from missionaries. They're not translating it to English first, but it's even cooler than that. You start dreaming in the other language. That's when you know that you're there, because you're no longer translating. Your brain has so owned this other language that it becomes the language of your thoughts. So guys, really, if you want to know electrochemistry and if you want to know redox, you have got to make these words the language of your thoughts. Again, I doubt if you're going to get there just because we're going to do this so quickly. But what happens is eventually you understand oxidation and reduction without having to translate it in your brain. Again, I don't think you're going to get there. Some of you might. But guys, it is critical that you understand these words. So guys, let's talk about them. Oxidation, by definition, is the loss of electrons, and reduction is the gaining of electrons. So guys, probably for you this year, you're always going to have to go through this translation phase. So what's going on here? That's losing electrons. That's oxidation. What's going on here? That's gaining electrons. That's reduction. Because when you really get good at this, you don't have to think about it anymore. You just go, oh, that's oxidized. That's reduced. Because it may be helpful for you to understand where these terms come from. So guys, why do we call the loss of electrons oxidation? I'll bet you can piece it together. What's obviously the element this is based on? Oxygen. So guys, let's talk about oxygen. How many valence electrons does it have? 6. So how many does it want? 2. What do you know about its electronegativity given where it is on the periodic table? It's strong. So guys, think about it. Oxygen is small and strong and has locations for 2 extra electrons, and it's everywhere. And so guys, when they first started studying electron transfer reactions, they found that everywhere they looked, oxygen was involved. And oxygen was just running around stealing electrons from everybody. So they said, why don't we call the loss of electrons oxidation? Because it seems like this is what oxygen is doing to everybody else on the planet. Do you see the connection? So why then do they call the other reduction? You're gaining a negative charge, so the charge goes down. It's reduced. So, guys, if you need a way to memorize this, this is what I go with. My rule of thumb is this. The charge of the atom that is reduced is reduced. It's a cumbersome enough sentence that I can remember it. If you go to the University of Utah, they will teach you oil rig. They think this is creative. Oxidation is loss, reduction is however you want to do it. Guys, you need to know that oxidation is the losing of electrons and reduction is the gaining of electrons. Now, with that said, the thing that's interesting about this, and it's sort of obvious, guys, you can't have one without the other. You've always got to have both. If something's losing electrons, oxidation, they've got to go somewhere. They don't just hang out. So anytime you have oxidation, you will also have reduction. It always happens in pairs. And because it always happens in pairs, we take oxidation and reduction and we bring it together into the combined term redox. So if you're talking to a chemist and you ask them about redox chemistry, they understand that you're talking about oxidation reduction chemistry. So guys, this leads us to some terms that you need to know. And it's the terms that refer to what are called agency. If you want to scratch this down, you can. But guys, you are going to run into the words oxidizing agent and reducing agent. When you see the word agent, you now need to be thinking about what it does to the other guy. So the oxidizing agent causes oxidation in something else, so it is reduced. And the reducing agent is the thing that causes reduction in something else, and it is therefore oxidized. Now, guys, the chances are good that you're reading those sentences and you are not visualizing what this means. The reason is because redox hasn't become your thinking language. You're trying to figure out how oil rig interrelates with all of these ideas. But guys, fundamentally what you need to understand is when we talk about agency, we're talking about what it does to the other thing. So if you are an oxidizing agent, you're causing oxidation in the other guy, which means the other guy's losing electrons, so you're gaining electrons, which means you're being reduced. And then guys, similarly, if you're a reducing agent, you're causing reduction in the other guy, which means the other guy is gaining electrons, which means you're losing electrons, which means you're oxidized. Do you see the distinction? So guys, let's do this. Where on the periodic table would you find the elements that are really good oxidizing agents? Where would they be? Talk to the person next to you. Where are the good oxidizing agents? Then guys, follow-up question. Where do you find the good reducing agents? Talk about that. All right, let's do this. So guys, let's chat. So think through this. Oxidizing agent cause oxidation in the other guy. So if I'm an oxidizing agent, what am I doing to this guy? Stealing his electrons. So an oxidizing agent causes oxidation in this guy, so I'm stealing electrons. Who are our good electron stealers? These guys. Then guys, a good reducing agent is good at causing the other guy to be reduced, which means I've got to give them electrons. So who are our good electron donors? Bottom left. You got the idea? You will see questions generically about that on the test. Well, they'll say which of the elements in this list is the best oxidizing agent. And that would be the ones that are in the top right. Obviously not the noble gases because they're full. And then your better reducing agents are down here. You guys good on that idea? Is that all right? Okay. So guys, with that said then, what we need to do is we now need to start talking about oxidation reduction reactions. So guys, scratch this down big and bold on your paper. So guys, again, we did talk about this stuff back in chapter 4. So we're going to do this as if it's review. So classic single displacement reactions, zinc and hydrochloric acid. Hydrogen gas is released, zinc chloride goes into solution. But guys, it turns out that this is also an oxidation reduction reaction. So let's talk about how this works, which means we have to do what? Draw a beaker. Come on. Draw a beaker with me. So guys, we got our beaker, and inside of our beaker, we've got our HCl, and our HCl is hydrogens and chlorides. We're not going to do hydronium. Now guys, what we've got to do is we have got to stick all right, we'll stay with that. Stick a bar of zinc in this. Zinc is a solid, and we now have a chunk of zinc, a bar of zinc, bathed in hydrochloric acid. So guys, these are our reactants. Now what I want you to do is draw another beaker and draw the products. So over in your right-hand beaker, draw your products. So what are our products? Well, I'm going to keep the zinc there because it's not all going to go away. But guys, what about chloride? Well, kind of. Guys, chloride starts in solution, chloride ends up in solution. What does that make chloride? Yeah, so we don't even need to talk about chloride because it's a spectator. But guys, what do we have over here in our product vessel that we didn't have in the reactant vessel? Good. Yeah, zinc ion You know what? I want to write that a little lower because I'm going to need a little bit of space there. So guys, one of the things that we have in solution is zinc ion. And then guys, what's the other thing that we have? H2. We have hydrogen gas that is going away as bubbles. So guys, the question is, what is going on between here and here that makes that change? Well guys, look at the two changes that are taking place. Zinc is going into solution. And when zinc goes into solution, what happens to electrons? The electrons go away. Guys, in its elemental form, do you remember this? In its elemental form, all elements have a charge of 0. So zinc has 0 charge as an element, but when it goes into solution, it loses electrons. How do we know the zinc is losing electrons? Its charge becomes +2. So then, guys, the question is, where do the electrons go? They go to the hydrogen, and hydrogen grabs the electrons. But guys, check this out. How many electrons does zinc lose? 2. But now look at how hydrogen takes them in. So one hydrogen takes in an electron, but in order to make H2, 2 hydrogens take in electrons. They then bond together covalently and they leave. So guys, we're going to talk about this later, but this is actually the law of conservation of electrons. You don't lose electrons in them. You've got to account for them. So guys, fundamentally what we've got going on is zinc, each atom of zinc is losing 2 electrons. Is that oxidation or reduction? Oh, come on. That's oxidation. So zinc is being oxidized. It's losing electrons. Where do they go? They go to hydrogen. Hydrogen gathers in those electrons, turning into H2 gas, and then going away, and that would be reduction. Do you see it? Okay. So guys, if you see it here, the question then becomes this. How do we represent this without having to draw beakers? Ready? Draw in the charges with me. What is the charge of zinc in its elemental form? 0. What is the charge of hydrogen in hydrochloric acid solution? 1+. Chloride is 1-. Or -1. They'd let you do it either way. But now, guys, what about zinc over in the products container? Zinc is 2+. We know that because it's dissolved in water. Chloride is still 1-. But now, guys, what about the hydrogen in H2? 0. This is its elemental form. So now, guys, here's what we do. We cross out our spectators. And now, guys, what we do is we look for charge changes. And I like to do this by drawing arrows. So zinc changes charge and hydrogen changes charge. Now, guys, what I like to do is I like to draw electrons on the line. So how many electrons is zinc losing? 2. So I like to just remind myself, zinc is losing 2 electrons. But now what about hydrogen? How many electrons are being taken up by the hydrogen? Also 2. Do you see that it's 1 per hydrogen, but the stoichiometry is 2 hydrogens? Is that okay? So now, guys, this, and I want you to write these answers down on your paper. What is being oxidized? What is being reduced? Write it down. Blank is being oxidized. Write a sentence. Blank is being oxidized. Blank is being reduced. Please scratch it down. Commit to an answer. You okay? So guys, let's remind ourselves. Oxidation is the loss of electrons. So what is being oxidized? What is losing electrons? Zinc. So the first question, zinc is being oxidized. Now, reduction is the opposite. Reduction is the gaining of electrons. reduction is the gaining of electrons. So guys, zinc is being oxidized. What's being reduced? Not hydrogen. Hydrogen ion. And guys, those are not the same. If you don't understand why those aren't the same, guys, you gotta pay, this is important. Guys, what is a hydrogen ion? It's a proton. Protons are not the same as hydrogen gas floating around in the atmosphere. Protons and hydrogen gas are so completely different. So the thing that is being reduced is hydrogen ion. It is not hydrogen, it's hydrogen ion, and it's important that you understand the difference. You guys okay? Questions about the fundamentals of oxidation reduction? Okay, then guys, finally notice that the number of electrons gained is equal to the number of the electrons lost. You're okay with that idea? Okay, so guys, we then just answered all of these questions. You guys good on those? All right. So guys, now what we need to do is we need to dig into this a little bit deeper. All right, let's just do this. So guys, you know how in general chemistry, we were always giving you steps for things? Steps to find the limiting reactant. Steps to solve mass problems. Have you ever, it was like everything in general chemistry had steps. Guys, think of the last time you got steps in this class. Never. That's what makes AP Chemistry so hard, is there aren't steps. There isn't, here are the things you need to do in order to be successful. It's, here's the big ideas, apply them in areas where you've never done this before, and then on the test, do it again. Well, guys, guess what's coming? Steps. You ready? So, guys, do not write this down, but here's where we're at. Up until this point, we've discussed balancing reactions, right, in order to support the law of conservation of mass. And we're still doing that. But guys, what we're going to learn to do now is balance redox reactions. And when we balance redox reactions, we're not only supporting the law of conservation of mass, we also have to support the law of conservation of electrons. This is horrible. Guys, I'm going to tell you right now, I've been doing this in front of students for more than 20 years. And 3 years ago is the first time in my career I've done this without making a mistake. This is crazy. So guys, you are not going to see this on the AP test. There might be pieces of this that they put on the AP test, but you will not see what you're about to learn in its entirety. So why am I teaching this to you? Because you are going to see it in college and it's miserable. So you may as well learn it from me instead of learning it later. But guys, this is what we're going to do. We are now going to learn to balance redox reactions. You ready? Here are the steps. Write them down. Step number 1. Write down the 2 half reactions. And you don't know what that means, I'll tell you in a minute. Then guys, once you've got the half reactions written down, you are going to balance the half reactions. In order to balance the half reactions, first of all, you will balance all the other elements besides hydrogen and oxygen. Then you will balance the oxygens by adding water. Then you will balance the hydrogens by adding protons. Then at this point, you will balance the charges by adding electrons to the side with the greatest overall positive charge. Then at that point, you will multiply each half reaction so that the number of electrons in both of them balance. Then you will add the 2 half reactions together and simplify, and this then gives you your balanced equation. However, if it's in a basic environment, you will then add hydroxides to both sides in order to get rid of the excess hydrogens. Then you'll check your work, curl in a ball, and weep like a child. What's up, Spencer?
So I
Does that mean you're going to do this instead of me? Come on. I dare you. Good. Yep. That's exactly what we're going to look at. Yep. And then what's the other half reaction? Good for you. Yep. And that's actually exactly what we're going to look at as our example for half reactions. So guys, this process is icky. So what we're going to do, as Spencer just described, is first of all, we're going to learn what half reactions are. Then once you know what half reactions are, we are going to apply this process to two different redox reactions. If I can get through either one of these without making a mistake, we'll do a little chemistry dance, and then we'll call it a day. You guys ready to go on? Do you still need me to wait? You guys okay? Not yet? I know, it's a lot of stuff. All of a sudden you were wishing there weren't steps. Oh yeah. Are you done? Can you just shoot a picture of it? It's in the notes. All right, I'll give you another second. Oh, yeah. If you forget, I'll remind you, because I'll be up here crying, and you can just join me. All right, you guys ready? So let's do this first. Don't write this down. You're going to get this quickly. But guys, we need to talk about half reactions. So what is a half reaction? Again, don't write this down. So guys, anytime you have a redox reaction, you can't have one without the other, right? So let me go up. So we understand that we can't have one without the other. So we understand, without even the things here, that we had one process that was losing electrons, another process that was gaining electrons. Well, guys, those things are what we call half reactions. So we can take a redox reaction and we can say this is the part of the reaction that's losing electrons, the oxidation. This is the part of the reaction that's gaining electrons, the reduction. And we can write them separately. Those are called half reactions. So Spencer, here's exactly the one you were looking at. So guys, reminding ourselves here what happens, zinc loses 2 electrons, hydrogen ion gains 2 electrons. So guys, what we can do is we can write 2 separate reactions that represent that. So this is the way we do this. So let me just get rid of this and start up here. So guys, zinc is turning into zinc ion. Because when zinc turns into zinc ion, what does the zinc lose? Electrons. How many? So plus 2 electrons. Now guys, where do those electrons go? Well, they go to hydrogen ion. So 2 hydrogen ions grab 2 electrons and they turn into hydrogen gas. Guys, these are the half reactions. Do you see how these work? Notice this though. Guys, we do not write this like this. You never write half reactions subtractively. So you don't say zinc loses 2 electrons to make zinc ion. That is in fact what's happening. But it's not zinc minus electrons. It's zinc turning into zinc ion, and then the 2 electrons are represented as a product. So guys, when you write half reactions, they're always written additively. They're never written subtractively. Now here's the question. Which one of these, top or bottom, is the oxidation? Oxidation is the top one. And notice in the oxidation, electrons are the product. In reduction, the electrons are the reactant. Does that make sense? Okay. Here we go. You're good on that? This is it, guys. We are going to balance this reaction. It's the iodide ion and the iodate ion yielding the triiodide ion. And we're going to balance this. Here's the rule. Just like chess, it doesn't count until I take my pen off the screen. So I get to make changes up until the point my pen comes off the screen. At that point, and if I screwed up, I screwed up. Oh, this is horrible. You ready? This is ridiculous. Do this with me. So guys, we are now going to balance. So here for a second. This isn't going to work. You need a clean sheet of paper. Oh yeah. Guys, these usually take about 10 lines to balance. Yeah, it's ridiculous. So guys, here we go. Step number 1 is write the half reactions. And now you're going, wait, we only have one product. Well, guess what? Both of the reactants turn into that product. So here's what you do. Okay, I need a very thin, we're going to go with blue because that's a little more soothing. And then guys, what you want to do is divide your paper roughly in half. And then you're going to put 1/2 reactions centered in that column on each side. So we've got I minus yields I3 minus. So that is one of our half reactions. The reactant turning into the product. Then guys, on the other side, we're going to have our other reactant, IO3 minus, yielding I3 minus. Now, last year I actually screwed this up. But in my defense, I was sitting in my sweats at home doing this over Zoom, and it was a train wreck. So have I screwed up yet? I minus to I3 minus, IO3 minus to I3 minus. Okay, so now we've got our two half reactions. So now guys, what we've got to do is balance these half reactions. So what do we balance first? Elements other than oxygen and hydrogen. So guys, it goes like this. We have 1 iodine here, we have 3 iodines there. So we balance that by doing this. 3I minus yields I3 minus. This makes me so nervous. Okay, so I didn't screw that up. Then guys, over here on the left, 1 iodine, 3 iodines. So we got to go 3IO3 minus yields I3 minus. You good? Have I screwed up yet? Okay. Now guys, the next thing we need to balance is oxygens. This is weird, but trust me. There are no oxygens in this, right? Rewrite it even though you're not changing it. So guys, 3I minus yields I3 minus. What you want to do is you want to work these in lockstep all the way down. So even though we didn't change it, we're going to rewrite it. So now on the right, we need to balance the oxygens. Now guys, how many oxygens do we have as reactants in the right half reaction? We got 9. So that means we need to add 9 waters to the product side. So we have 3IO3 minus yields I3 minus plus 9 Wawas. Okay, still haven't screwed up. I'm doing good. Okay, now we need to balance hydrogens by adding protons. Again, we don't have any on the left. we're still going to rewrite it. Okay, now we have 18 hydrogens. So we need 18 hydrogens plus 3 IO3 minuses yields I3 minus and 9 waters. We okay? Good so far, right? Okay. So now, guys, and this is where I tend to make mistakes. Now we need to balance the charges. And we do that by adding electrons to the more positive side of each half reaction. So guys, I have a slight advantage over you in that I can change colors. But this is what I like to do. What is the total negative charge on the left for this reaction? -3. You have 3 -1s, that's -3. Then guys, what is the negative charge on the right? -1. This whole I3 has a -1 charge. So what we need to do now is we need to balance those charges. And the only way we can do that is by adding electrons. So we need to bring this charge down to -3. So to do that, we are going to add 2 electrons. Did that make sense? Okay. And I haven't screwed up yet. All right, so now guys, on the left, the right half reaction, reactant side, so 18 minus 3, is that right? So this is plus 15. Why does that feel wrong? That's right? Okay. Then on the right, we just simply have a charge of -1. So now, guys, what we've got to do is we've got to make these equal, but by adding electrons. So which side do we add electrons to, the left or the right? Left. And how many? 16. So, guys, what I'm going to do is just create a little more space for myself and then go plus 16 electrons yields that. Sorry, that's really sloppy. Oh, it gets worse. Yeah. Okay, so now, guys, this is a great time to stop and talk and then check. So first of all, this. You know how I told you that they will never ask you to do this on the test? This they will ask you to do on the test. They might give you this half reaction and say balance it. Or they might give you this half reaction and say balance it. But I've never seen an example where they've given you the entire reaction and said balance it. So they may ask you to balance a half reaction, but I've never seen where they've asked you to balance the entire system. So with that said, they will also do this. Guys, looking at the reaction on the left, is that oxidation or reduction? How do you know it's oxidation? Losing electrons. What about the one on the right? Gaining electrons. Now, guys, what about this? What if you had electrons as a product on both sides? You screwed up. You can't have 2 oxidations. If this guy's losing electrons, the other guy's got to be gaining electrons. So when you get to this point, it's a good time to stop and make sure that you've got electrons on both sides of the half reactions. One on the left, one on the right. If you've got a place where they're both reactants or both products, you know you screwed up. But we're okay. So now, guys, what do we need to do? We need to now make the electrons balance. So we got to multiply the entire left-hand half reaction by 8. Oh, yeah. Here we go. Back to blue. So we now have 24 I minuses yields 8 I3 minuses and 16 electrons. You good? Because we need the electrons that are being lost and gained to be the same. So when we were here, we had 2 electrons here and 16 electrons here. So we needed to multiply this entire thing by 8 so that the number of electrons coming out equals the number of electrons going in over here. Okay. Now, guys, at this point, it's time to mesh these together. So you'll notice I told you before, right? Always rewrite these if you're not making changes. This is the one time where you don't need to do that, because you're now going to bring everything down. So what you're going to do is you're going to write down all of the reactants from both half reactions. So 24 I minuses, and that's our only reactant here. Then we've got to grab these reactants, plus 18 hydrogens, plus 3 IO3 minuses, plus 16 electrons yields. Oh, yeah. Then, guys, we get our products. 8 I3 minuses plus 16 electrons plus an I3 minus plus 9 waters. Shoot, am I good to there? Whew. All right, I'm sure I'll still screw this up, but here we go. All right, so then, guys, what we're going to do is simplify. If this doesn't happen, you screwed up. Then over here, those are all sort of on their own. So we don't have iodines on each side. We don't have IO3s on each side. So really, the only thing we can do to simplify is bring these together. So we've got 9 I3 minuses plus 9 waters. And then over here, we've got 24 iodides, 18 protons, and 3 IO3 minuses. Now, guys, we're still not done. Because everything's divisible by 3. You see it? So this would actually be, I hope you don't mind, I'm just going to erase this out of space. So divide everything by 3, and we get 8. And then 18 divided by 3, we get 6. And then 3 divided by 3 just goes away. And then we get 3 is there. Oh, guys, I think I did it. So now we need to make sure that this does in fact balance. So how many iodines do we have on the left? Well, 9, right? We've got 8 plus the 1 right there. So iodine atoms or ions, we have 9. And over here we have 9. And then we've got 6 hydrogens here. And we've got 6 hydrogens there. And then we've got 3 oxygens here and 3 oxygens there. Ah! I did it. I did it. You don't even care. I'm excited. So, guys, that's it. What a disaster, right? Oh, I just did it. That was it. And the inside. That's right. So, guys, let's do this. I want to do one more of these with you. There really aren't questions, right? Okay. So, guys, we're going to do one more, but this is not the same. So how is this different? Well, now we've got 2 reactants and 2 products. But also, importantly, we have a basic and not an acidic environment. Now, guys, notice back here on the one that we solved previously, this was in an acidic environment. I'm not going to switch back to the previous slide. But guys, this one that we solved a minute ago was in an acidic environment, which meant that that's okay. That's what acids do, is they produce free protons. Well, guys, you can't have free protons when you're in a basic environment. So how do we deal with it? The answer is at the very end. So here we go. Do this with me. Right in the middle. Squiggle. We'll stay with blue. Little squiggle down the middle. And then, guys, write your half reactions. Do it without me. So on the left, we have copper ion becoming copper metal. And on the right, we have N2H4 yielding nitrogen gas. You know what? I'm going to move that over a little. This doesn't count as a mistake. N2H4. Okay, like so. So guys, by the way, we can actually answer one of these right now. Is this oxidation or reduction? Copper 2 plus becoming copper 0. Its charge is being reduced. So that's reduction. And guys, we'll see that more clearly in a minute, but we know that the one on the left is reduction because copper is going from a +2 charge to 0 charge. Its charge is being reduced. Okay, so let's do this. The first thing we need to do is balance elements other than hydrogen and oxygen. Ready? Done. Don't rewrite it if you don't have to do anything to either one. So that's done. Now we balance oxygens by adding water. Done and done. Good? Now we balance hydrogens by adding protons. That one needs some help, so we are going to rewrite this one. Then we need to balance hydrogens, so we've got N2H4 yields N2 and 4 protons. I got you. Oh, you got it? Okay. So guys, are we all ready to balancing charges? We've done elements, we've done oxygens, we've done hydrogens. It's now charges, right? All right, so here we go. Switching colors. This is +2. This is 0. So we need to add 2 electrons to which side? The left. So 2 electrons plus copper ion yields copper metal. That is our reduction, the gaining of electrons. Electrons are a reactant. Then over here, this is 0. This is 0 and +4. So we need to add 4 electrons to the right. Is that okay? So forgive me, I'm just going to shoehorn this in there. +4 electrons. Now guys, at this point, we need to now balance our electrons. So we need to multiply the left by 2. So we have 4 electrons plus 2 copper ions yields 2 copper atoms. Am I okay? Is that right? I think that's right. Okay, so then guys, at this point, we're ready to bring them together. So we go 4 electrons plus 2 copper ions plus an N2H4. Again, we're grabbing the reactants from both half reactions. Yields 2 copper atoms plus a nitrogen molecule plus 4 hydrogens plus 4 electrons. Starting to get cocky. Am I okay? I think I'm okay. I feel okay. All right. So now, guys, yep. Not at all. No. Okay, so now, guys, we cancel what we can. If our electrons don't go, we know we made a mistake. And that's really what we're left with. And it doesn't reduce because we've got things with ones. So, guys, that's the balanced equation. If it were in an acidic environment. But, guys, this is not in an acidic environment. This is in a basic environment. And in a basic environment, you do not have an abundance of hydrogen ion. What do you have an abundance of in a basic environment? Hydroxide ion. So here's what you do. You add as many hydroxides to both sides of the reaction as you have hydrogens. So we are going to add 4 hydroxides to both sides. So when we do that, we get 4 hydroxides plus 2 copper ions plus an N2H4. So we added 4 hydroxides to the left. Now we're going to add 4 hydroxides to the right. So we get 2 coppers. We've got our nitrogen molecule. But then, guys, when we add 4 hydroxides to 4 hydrogens, what do we get? 4 waters. That is our balanced equation. So let's check. We've got 4 oxygens, 8 hydrogens, 2 coppers, 2 nitrogens. Boom. I'm tired. What do you think? Yeah. So, guys, that takes us through the end of our day. This, then, is your homework. Guys, 2 more homework assignments this year. Right? This is unbelievable. So we will take a break when it's time. We're going to come back, guys. When you get back, please gather up everything that you have relative to the lab that's in process, the titration lab with your graphs. Grab up all of that stuff. Do not grab computers. You can use them later, just not now. And guys, we'll take a break when the bell rings.